Let's talk about magnets. First of all, in the same way that charges come in two types, negative and positive, magnets are dipolar. They come in two poles. Does anybody know what the poles are called? We also use them in geography. We call them north and south. We'll use capital N as our abbrev for north and capital S as our abbrev for south. In other words, if this is a magnet here, a bar magnet, we would have a north pole on one side and a south pole on the other side. In the same way that like charges, like poles repel, unlike poles attract. If you've ever played with a magnet and tried to force it together and felt it resisting you, it was because you were trying to push a north towards a north or a south towards a south. However, unlike electric charges, you can't isolate a north pole and a south pole. You can isolate a negative charge, we call that an electron. You can isolate a positive charge, we can isolate a negative charge, we call that an electron. You can isolate a positive charge, we call that starts with letter P, proton, okay? We can isolate those. You can't isolate magnetic poles. What would happen if we cut this magnet in half? If we snapped this magnet in half, if we broke it apart, we would end up with a south pole right there and a north pole right there. Magnets send out invisible but detectable magnetic field lines in the same way as charges send out invisible but detectable electric field lines, in the same way as masses send out invisible but detectable gravitational field lines. And because we have the same issue as electricity, with gravity, everything fell, but with charges, like charges, stuff could fall up. With magnets, like poles, we're going to have to define the direction of the magnetic field. For the electric field, we said which way would a positive want to move if it could. For magnetic field lines point from north to south. Or if you happen to have a compass handy, it's the direction a compass points. Compasses point south. Wait a minute, Mr. Dueck. I have a compass, and I believe it points north. No, compasses point in the direction of the magnetic field, and magnetic field lines go from north to south. Compasses point south. Mr. Dueck, I don't mean to be pedantic here, but I was in Scouts or in Girl Guides, and I'm pretty sure my compass points north. It points geographic north, which happens to be magnetic south. At the top of the Earth on our map, there is a geographic North Pole. Underground, there is a magnetic South Pole, because magnetic field lines point from north to south. We'll talk about that in a second. What symbol do we use? What letter do we use for magnetic fields? Why can't we use M for magnetic fields? Okay, why can't we use F for fields? So we yoink a Latin word. The symbol for magnetic field is a capital letter B, and it's a vector. It has direction from north to south. And hey, you know what? You get to learn a brand new unit today. Magnetic fields are measured in Teslas. Symbol, capital T. There is another magnetic field measurement, Gauss, and that's used in a different application. So if you do a Google search, what are the SI units for magnetic fields? You'll see probably both Tesla and Gauss, but we're going to use Teslas. Earth's magnetic field is around 10 to the negative 5, 10 to the negative 4 Teslas. It varies because as you get further from the Earth, it gets weaker. A very large magnetic field, 1 Tesla is massive. None of you could pull apart 2 1 Tesla magnets. Not even close. In fact, in an MRI machine, which the M stands for magnetic, those have very strong magnets. Those are about 4 Teslas. Put your pencils down, look up. Here's some people late at night. They're very careful to stay out of frame because I'm guessing they didn't want to get fired. They are playing around with some magnets. So Mr. Dueck, let's go details. Let's go like that. What did I call this one? Metal objects. So this is a 4 Tesla magnet, which is really big. Come on, computer, you got this. The video? Oh, yeah. Try it again. Come on, computer, you got this. Sorry, YouTube. This is going to be irritating. Oh, now you're going to work. Okay. Now you've opened twice. That's just going to be irritating. So let's try one more time. My old computer was much better. There we go.
Ooh, baby! You see this? Whoa!
Your head's not a problem. There's very little metal in your head. Despite what your parents
So
say.
the force we're reading on that guy right now, just at that part of the magnet, is
So we have a 300-pound force gauge.
close to 300, 280.
And you'll see we have a wrench, a metal wrench, just hovering in midair as the magnet is exerting a force on it.
We forget.
That guy.
Now, it's not quite centered. There's a slight imbalance, so you'll suddenly see it clank to the side.
400 now.
Wait for it.
And it's going to attach itself to the board here in a second.
Any second, it's going to start dropping, yeah. Gravity will just do enough.
There it
There
goes.
it goes. Oh, that's almost
And
600.
now, it is giving us a reading of
500.
500.
So for you to pull that wrench out of there, you would need to be able to lift 500 pounds. And that's 4 Teslas. That's why I said a 1 Tesla magnet, none of you are getting apart. That's very strong.
Pound.
Hey, let's try a chair, shall we? Yes, we shall. Weight is not the correct. There's no mass involved here. It's a field. It has no mass. It transmits magnetic force. What you're asking is, how strong is the magnetic force? That's tomorrow, well, Tuesday's lesson. We'll learn how to calculate the force. Today we're going to talk about how to interpret it. Oh, Tuesday's the test, Thursday's lesson. Okay, so we've got a chair. Wait for it. Okay, the chair is kind of hovering there. It's got some metal in it, some plastic, but some metal.
50, 560. Whoa. Ooh. We are at 700.
700 pounds.
Yeah.
It's meant to experience 700 pounds of force.
700 pounds.
Oh, it's about
Oh, and we have jumped to 1300.
that's exactly what I'm about.
Yeah, we have
Well, the
jumped.
most magnetic stuff is right here, still on the top of the chair.
Whoa.
So
I
we're
mean,
just about to hit the sweet spot.
The
Keep going.
wheel is sitting.
Whoa!
Baby!
There we go.
Oh my god.
Okay. What do we got now? No, look at it. 1700 pounds.
We are at 1700,
Wait, once
which
again,
is far
250.
more than this thing.
You just relaxing it now?
Yeah.
Okay, so the there it goes. Oh, 1800.
1800.
It's past 2000. I'm past 2000.
Just shy of 2,000 pounds. So here is your public service announcement. If you are ever put into an MRI machine, if you have any piercings, tell the technician, even if you're embarrassed, because if you don't tell the technician, they are coming out. They are coming up, and if you talk to technicians, many of them will have embarrassing stories of someone who didn't say anything, and then there's a mighty scream. Yes, it came out. It's coming out in the most horrible way possible. Okay? So 1 Tesla big, 4 Tesla, holy smokes. I think the record for the largest electromagnet is around 40 Teslas. And I think I have a video, but that throws out such a strong magnetic field that it wrecks the camera. So the video only lasts a short while. Oh, that I'd have to look up. Good question. Yes, what would a quasar be? Bigger, probably. There are 2 main types of magnets. There are permanent magnets, like the ones that you put on your refrigerator, like these rare earth magnets, like the ones that look like a horseshoe. We call those ferromagnetic materials. They're made from ferromagnetic materials. There are certain metals on the periodic table that you can magnetize. But the second, even more useful type are what are called electromagnets. This is a magnetic field caused by a current. This is really useful because it means you can turn a magnet on and off. Hugely useful. Oh, and you can control the strength of the magnet by controlling the strength of the current. And we've just finished a unit on circuitry. Yeah, by changing the resistors and the voltage, you can get whatever current you want. Let's go back to our bar magnet. What would magnetic field lines look like around the bar magnet? What do magnetic field lines point from? What to what? You can see the arrows are going from north to south. If you brought in a compass and you put it right here, it would point that way. Don't write that down. If you brought in a compass and you put it right there, it would point that way. If you brought a compass right here, it would point that way. Compasses point in the direction of magnetic field. They point south. And again, I see some of you, but I learned that a compass points north. It's way more cool and confusing and badly named than all of that. So we'll dive into that in just a second. Another note, magnetic field lines have no beginning and no ending. Unlike electric field lines, which came to a stop on a charge, magnetic field lines, if you ask me, technically inside the magnet, they continue, don't write this down, but they continue going that way. They're not circular. I don't want to call them loops, but they are connected. They're a closed path. Okay. The Earth is also a magnet. That's how a compass works. In fact, I have a compass right here. Let me pause the video for a second. If magnets point from north to south, what does the magnet inside the Earth look like? Like that. We call this geographic north. Even worse, we actually, if you're taking a navigation course, you'll call this magnetic north. It's not. It's magnetic south. But the nomenclature they use from sailing, if you take a navigation course, you'll distinguish between geographic north, which is the actual North Pole, magnetic north. That South Pole, which we stupidly call magnetic north, isn't right on the North Pole of the actual Earth. It's a little bit off. Right now it's in Canada. It's slowly moving towards Russia. And once it reaches a certain point, I'm sure Russia will claim it as theirs. Why would you care? It's a whole trades, international routes. It's more complicated than you realize. If you buy, for example, I have a boat, if you buy a navigation chart, it will actually have the offset between what magnetic north, magnetic south is, and geographic north, and you have to adjust that on your charts. Nowadays with GPS, it's not such a big issue, but back even 20 years ago, it was.
What makes it the same?
That's a great question. Julian asked, why does the Earth's magnetic field roughly align with its rotation? I don't know. I suspect it's because, so we believe that that magnetic field is caused by, we believe there are two cores inside the Earth. Once you get past the mantle, we think there's a metal core and another core, and they're spinning and they've kept their momentum. And we think that interplay is what causes the Earth's magnetic field. And I guess spinning in the same direction that the Earth along the same axis would make sense because that's the momentum it would continue to have. Anyways, like I said, it's complicated. Spoiler, this would make a lovely multiple choice test question. What does the magnet inside the Earth look like? South is at the top. It's also good nerd trivia. Example 1 says, draw the magnetic field lines below. Okay, like poles. So if I start on this magnet right here, I would get repelled by the north. I would end up maybe like that, and I would end up like that. Maybe like that, maybe like that. Now, magnetic field lines have no beginning and no ending, so that top left line would eventually come in over here, and that top right line would eventually come in over here, coming over here, coming over here, and I could continue this, but I have some pictures that were drawn with computer graphics that'll look better. So we're not going to draw this. We will interpret these diagrams, but I won't ask you to draw these diagrams. Symbols. We're going to get into three-dimensional vector questions in this unit. We're going to just have to deal with three-dimensional objects, but it's tough to draw a three-dimensional object on a flat piece of paper. So we're going to use an arrow pointing left for left, an arrow pointing right for right, an arrow pointing up the page for up the page, an arrow pointing down the page for down the page. But we're going to need to show into the page and out of the page. How are we going to do this? To show out of the to show into the page, we're going to use a circle with an X. That's meant to be the tail feathers of an arrow retreating away from us. So imagine an arrow pointing, like an actual archer's arrow, pointing into your page. You would see the tail feathers. Sometimes if I'm typing the graphics, because it's really, really tough to get the graphics for a circle with an X inside of it, but it's really easy to do a capital letter X, I might just do that if I'm typing the graphics because it's just a pain. But when we're handwriting, that's into the page. To show out of the page, we reverse it. We imagine the tip of an arrow coming towards us. What would that look like? It would be a circle with a dot. That's meant to show out of the page towards us. You'll need to memorize these symbols, but I'll be throwing them at you enough that I think you just will. And they kind of make sense. Oh, as before, if I'm the one doing the computer graphics, because it's really hard to get a circle with a dot inside of it, I may just do a bunch of dots. That I can do, periods, a bunch of those, and that will be meant to show out of the page in my rough diagrams. But if I get good diagrams, they'll look like that. Or if I'm handwriting, I'll do that.
So you just be using a lot of brackets.
You'll, for multiplication, patience. Let's talk about electromagnets. It turns out a current carrying wire generates a magnetic field. In other words, if you have a wire carrying current and you bring a compass nearby, the compass will get deflected. What direction? We're going to learn what are called right-hand rules. There are 3 of them. They're actually all part of one Uber rule, but we're going to look at 3 right-hand rules. And what that means is you're going to have to keep your right hand, not your left hand, your right hand handy. Who are my lefties in this class? Who writes? This is one of the only times we have an advantage because we can have our right hand free and still write. You're not a lefty? Okay. You and I, this is where we are superior to everyone else. Everyone else is going to have to put their pencil or their pen down, do the right hand rule, then pick up their pencil, remember the answer, and write the answer. Here's right hand rule number 1. We're going to practice this a whole bunch, and you're going to need to memorize this. And I apologize to those of you on YouTube because you won't know what the heck I'm doing. Did I remember to hit record? Unpause? I did. If you point the thumb of your right hand, which hand? in the direction of the positive of the current, your fingers will curl in the direction of the magnetic field. So look up. Let's suppose this is a wire carrying current, and let's suppose it's carrying current to your left, that way. Everybody, imagine you're holding this in your hand, point your thumb in the direction of, right thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. Above the wire, the magnetic field would be going towards the front of the classroom. Behind the wire, the magnetic field would be pointing down towards the ground. Underneath the wire, the magnetic field would be pointing towards your face. And close to you, the magnetic field would be pointing straight up. If the wire was going this way, point my right, let's say, and the current was going towards the front of the classroom, everybody point your right thumbs towards the front of the classroom. Above the wire, the current would be going to the right-hand side of the classroom. On this side of the wire, the current would be pointing, magnetic field would be pointing straight down. Here, underneath the wire, the magnetic field would be pointing to the left of the classroom. On the left side of the wire, the magnetic field or compass would be pointing straight up. This is the right-hand rule. You may find it easy to hold something like a pencil or a pen to simulate the wire to help you visualize. We're going to practice this a whole bunch. Are you ready? An app, the current is going upwards. Everybody point your right hitchhiker thumb upwards. And then look at how your fingers are curling. That will be the direction of the magnetic field around that wire. As you get closer, it gets stronger. As you get further, it gets weaker. But we're just concerned right now about the direction. If I reverse the current, opposite direction. Okay. Oh, you don't yet, but we're going to practice a bunch. You ready? Here's a wire. What does this X mean? What direction is the current going? No. What? So everybody right now, do me a favor, because my screen is vertical, hold your paper up so it's vertical. All of you, hold your paper up like this so we're all on the same frame of reference. So you're going to point your right thumb in the direction of the current. I'll model it up here. What direction is the current going? All of you should be pointing your right thumbs like this. They should be pointing towards the front of the room because that's into the page. What direction is the magnetic field pointing above the wire? To the
Right.
What about to the right of the wire? Straight?
Down.
What about underneath the wire? To the
Left.
What about to the left of the wire? So we can sketch that. It says sketch the magnetic field. It's going to look like a circle. It's pointing that way, that way, that way, that way. We'll keep practicing. Okay? The further you got from the wire, the weaker the field. The closer you got, the stronger the field. But I'm telling you, if you put a compass above this wire, it would point to the right. Okay? Example 3. Okay. Now I'm giving you the magnetic field. What direction is the magnetic field above the wire? What do the dots mean? Out of the page. What direction did the magnetic field beneath the wire? What do the X's mean? So everybody, again, until we get good at this, you'll find it easier to hold your paper vertical to match my board, to match my screen. I can hold this wire this way or this way. Which one of those will my fingers match the direction of the electric field? Don't blurt your answer out loud. Try and figure it out. Which way will I hold this wire so that my fingers are pointing towards me, out of the page, above the wire, and away from me, beneath the wire? So I'm not looking. All of you should figure it out. I think you're going to find your thumb should be pointing to the right. Yes? That gives it out of the page, above the wire, into the page, beneath the wire. Is that correct? So what direction is the current flowing then? Okay. Okay. Back here. Thank you. We're gonna practice this some more. By the way, there's 2 more right-hand rules. This is why I told. Hey, you guys at least are here. I feel for the people on YouTube. What's he talking about? Pointing. Yeah. Sorry. Oh, the right-hand rule works for current, which is positive charges. If you have electrons, you can either use your left hand. I find it confusing. I just instead say this: an electron moving to the left is the same as a proton moving which way? To the right. An electron moving down the page is the same as a proton moving up the page. An electron moving into the page is the same as a proton moving out of the page. I just flip the direction and use my right hand. I don't memorize a left hand rule. Right hand rule works for currents, and because current is which way the positives would want to move if they could, it works for protons. Okay? Here's a picture of this right-hand rule I found online. You point your right thumb in the direction of the current. Your fingers curl in the direction of the force. That's rule number 1. Let's talk about an electric device called a solenoid. If we coil the same piece of wire around and around and around and around in many loops, all in the same direction, we call the resulting coil of wires a solenoid. What does a solenoid look like? Let me pause the video. It turns out you also get a magnetic field, because if one wire going in a straight line gives you a magnetic field, if you overlap them, you get a very strong magnetic field, an overlapping magnetic field. The question is, what's the direction? What would the direction of the magnetic field generated by a solenoid be? Here's a typical solenoid. We learned you can dramatically increase the strength of the magnetic field by putting an iron core in the middle. So that one that you see in front of you there, if I put a piece of iron in the middle, because now the iron also becomes magnetic, whoa, you get a nice strong electromagnet. A magnet you can turn on and off by dropping the current, by switching the current on and off, or that you can flip by flipping the current. Hugely useful. I said we call this an electromagnet. It has thousands, probably millions. Okay. A classic one that you may have seen in real life or on TV, those large magnetic cranes that pick up wrecks of cars where they're able to pick up the car. You'll notice they're always round shaped. That's because that is one big solenoid packed tightly together, and they can switch the magnet on and off. Direction. Right-hand solenoid rule. This is right-hand rule number 2. Imagine holding the solenoid in your hand. You curl your right hand fingers in the direction of the current. Your thumb points north. What? So, for my solenoid analogy, I'll use a tube like this. I imagine I'm holding the solenoid in my hand. The wires are going this way. The current can either be going this way, or it can be going this way. I hold it in such a way that my fingers match the direction of the current, and my thumb is pointing north inside the solenoid. Can I pause the video? This is such an awkward one to teach because I'm standing up. Nope, hear me on YouTube. Pause for. Let's do an example. Example 4 says, what direction is the magnetic field below? There is no solenoid in the picture yet because I also wanted to show you how you draw a solenoid. So a solenoid is a coil of wires. We want to make it look 3D-ish, even though it's on a flat piece of paper. Everybody look up for a second and pay attention. Niels, you too, just hang on to it. Everyone look up. Newer YouTube, everyone look up. Here's how you draw a solenoid. What you do are elongated letter S's or backwards letter S's. Watch. If I go like this, and like that, and like that, and like that, I get the effect of the wires vanishing behind and coming back to the front, and then I'll go like this. And then put your battery underneath so that the positive is pointing left. Okay. I could have drawn forwards letter S's or backwards letter S's, and they're long stretched out letter S's. That gives it kind of a 3D effect. Okay, once you've drawn that, label arrows for the current. So the current would be going in mine this way, and then I guess it ducks behind. You know what? It would come over the top. The current is flowing in that direction. Okay? I can hold this solenoid in one of two ways. Again, hold your paper vertical so you match mine. I can hold it in my hand this way, or I could hold it in my hand this way. Which one will my fingers curl in the direction of the current when my thumb points to the left or when my right thumb points to the right? Yeah, you know what? This is the only way I can hold this so that my fingers would curl over the top towards me as opposed to over the top away from me. That's the North Pole inside the solenoid. The magnetic field inside the solenoid would go like this. There's a North Pole right there, a South Pole right there, and the magnetic field points from north to south. Now, because it doesn't end inside the solenoid, it points that way, which looks like it's pointing from south to north. It's not, it's just continuing its direction. Also, the same thing underneath, in fact, in 3 dimensions all around it. Okay. This solenoid, by the way, having a magnetic field you can turn on and off, terribly useful. Do I have the oh, good. I was going to say, I'm sure I have a picture. Our fire alarm bells are solenoids. In fact, most of our bells that ring are solenoids. I wrote here, we use solenoids in transformers, the electrical device, not the toy, motors, generators, TVs, speakers, doorbells, fire alarm bells, cell phones, power door locks, etc. A friend of mine used to live in a building from the 1930s, and they had, this is their fire alarm bell. There's the solenoid right there. All they're doing is they're running an alternating current through this solenoid because that's what you get coming from your plug. So what happens is the current would go this way, then this way, then this way, then this way. You would get a magnetic field, attract, repel, and put this on a hinge so it goes ding, 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 attract, repel, attract, repel. Our fire alarm bells work exactly the same way, except they put the bell over the solenoid so people can't vandalize it. But if you pull that bell off the wall, you would see this is what was inside the bell. It's just now the clapper is ringing on the inside, not on the outside. Very clever device, very low tech. As long as you got power, you've got a fire alarm. The old telephones that used to actually ring had a solenoid inside of them. Yeah, I think I got an old telephone on the shelf still somewhere. I might have finally put it away. I took apart some old ones. I was given some old ones, and you could find all sorts of neat electrical devices. Car locks, power locks almost certainly involve a solenoid, where if you want the lock to go down, you attract. If you want the lock to go up, you repel. It's a little more complicated than that, but the original ones, that's what they did. They're all over the place. It gives us a way to create a changing magnetic field that we can turn on and off. Example 5. The conductor on the left carries current into the page. The conductor on the right carries current out of the page. Yeah, X means into the page, dot means out of the page. It says, draw lines of force around each conductor showing their direction. This is not the solenoid rule. This is going to be the first rule that we learned. So you're going to, let's do the wire on the left. Point your thumb in the direction of the current. Now you can do this one of two ways. You can keep your paper down, or if you want to raise your paper vertically so you match my board, I would be pointing my thumb this way, and I would say right here, which way is the magnetic field pointing? Down. Good. So I'm going to draw a circle around this guy. Magnetic field's pointing down. I think the magnetic field's pointing that way. Magnetic field's pointing that way. Magnetic field's pointing that way. Okay? Now let's repeat for the wire coming out of the page. Which way would the magnetic field be pointing to the left of the wire? Down. Let's draw another circle. I'll change colors. Down, that way, that way, that way. Okay? What's interesting is right here where the fields overlap. Are they what? Like fields? These wires would actually get pushed away from each other. And you have to take that into account when you're doing wiring, especially if you're going to be flipping a switch off and on, off and on, off and on, because you can have the wires constantly feeling this repulsive force. They can actually wear loose from their staples and become loose wires. So there's rules. You have to have staples or secure a wire every so and so many meters, in fact, less than that, every short distance to prevent this from happening. So would they attract each other or repel each other? They would repel each other. Why? Because where they overlap, like fields repel. Example 6, you know what? This is going to be the solenoid rule. How can I tell? There's a solenoid. I'm going to label the current. Oh, they already did label the current. Which end will be north? So this time, I'm not going to model it for you. You're going to have to figure it out with your right hand. Imagine holding that solenoid in your right hand. Niels, imagine holding that solenoid. I don't care what you're looking for. Stop right now. Imagine holding that solenoid in your right hand, all of you. Curl your fingers in the direction of the current. Addie's using a water bottle. That works. Which way is north, A or B? I agree.
Opposite this one.
Okay. Julian said it's the opposite. Don't try and memorize. You'll have to derive this from scratch in every picture, right? Because I can just tilt these or move these or whatever. Those are the two easiest right-hand rules. Ha-ha. Here's the third one. This is called the right-hand motor rule. This is the one where we're going to get three-dimensional. Okay? Suppose we have a wire that's carrying a current through a magnetic field. So there's the battery. So I guess the current is going in this direction. That's the letter I. Because it's going to have its own magnetic field, that magnetic field is going to interact with this external magnetic field. What do those dots mean? What is the external magnetic field direction? Okay. Out of the page. We'll say out of the page or into the page. Out of the page. That wire then will feel a force. It will feel a strong force. What direction? You ready? Watch me look up. David, look up. This is the tough one. You start out not with your fingers curled like the previous two, like you're hitchhiking and handshaking. Okay? You point your right thumb in the direction of the current. You point your fingers in the direction of the magnetic field. For me, I have to do this. Your palm points in the direction of the force. The force would be down the page. Now, if you find you're doing crazy yoga, you may find it easier to put your hand behind you and do it facing forwards. Current is that way. Field out of the page, my palm points down. So if you're getting really, really wrapped up, just stick your hand behind you. Okay? By the way, This is actually vector multiplication. There are two ways to multiply vectors. There's something called a dot product where you get a scale answer. Work is force dot distance. That's why work is a scalar. This is what's called a cross product. You would use a times sign, but in physics, you don't say times, you say cross. And it turns out, look up. Are you ready? Look up. That direction cross that direction is that direction. That direction cross that direction is that direction. That direction cross this direction is that direction. Your right hand is actually a built-in cross product. Okay? Oh, you use this right-hand rule, by the way, whenever you're putting in a screw. If I want the screw or the bolt to go this way, I turn it that way. If I want the bolt to go this way, I turn it that way. Those are designed to follow the right-hand rule for a current-carrying wire. This shows up all over the place. We need to practice this a lot. Example 7 says this. To find the direction of the find the direction of the net force on the wire. So let's interpret this. Here's the wire. What direction is the current in the wire? Not to the left. Look at the wire. What direction is the current in the wire? Into the page. What direction is the magnetic field? Although you'll notice, did I bother writing magnetic? No, I used our abbrev, capital B.
Oh, sorry.
To the left. So you ready? Let's do this one together. If you want to, you can use mine and hold your paper up vertically. I would point my right thumb into the page. Now, for me to point my fingers in the direction of the magnetic field, I could, you know what? I'll do that. Way easier. Just shoot your hand across. Which way is my palm pushing?
To the left.
Which way is my palm pushing? Up the page. Up the page. So you ready? If you're looking for stupid ways to remember, palm pushes. That's the force. Unfortunately, everything begins with an F. Forces feel. I don't have a good hook for this one, unfortunately, but I do remember my palm pushes. But start out with your hand. Hitchhiker, handshake. Don't put a 90-degree bend in it accidentally. You'll get confused. Put your pencils down, look up. Here is an example of a wire experiencing force. 12-volt car battery, on-off switch. And strong magnet. So, when we run a current through this wire, it should experience a force, and it did. What happens if we reverse the current? Not up, but yeah. Okay. I have a similar device. I'm going to need a couple of volunteers to give me a hand in just a second. Let me pause the video. An electron traveling to the right enters a magnetic field as shown. Okay. We have an external magnetic field. So this is going to be the third rule, what's called the right-hand motor rule, except we don't deal with electrons, we deal with positives. Which way is this electron traveling? To the? What's that the same as a proton traveling? To the? So everybody point your right thumbs to the left. What do those X's mean? What direction is the magnetic field? Into the page. So point your right thumbs to the left, fingers into the page. When the electron hits this magnetic field, what direction will it get deflected?
Down.
Next lesson, we'll learn how to calculate the magnitude of the force. All we're doing right now is getting the direction. Okay. If you want to get these wrong, get your hands away from you, get them nice and big, and you'll get the right-hand rules correct. When there was an old provincial exam, the very first year that I was teaching Physics 12, all the kids were writing the provincial upstairs. And I'd really drilled this with my students. Halfway through the exam, I got a call from the teacher upstairs. Mr. Dueck, you're going to be so disappointed. Your kids are giving each other hand signals. They're cheating. They've got some kind of code. So from that on, I explained to whatever teacher was supervising, look, about halfway through the exam, they're going to get to the magnetic section, and you're going to see them doing this. It's not a code, it's right-hand rules. A TV screen is actually just a bunch of electrons hitting the screen. If you bring a magnet nearby, it will deflect it. Don't do this with your TVs. It's not good for the TVs. Here's an old style cathode ray tube. These are the ones that had the big thing that stuck out of the back. Very simple technology, not the same as flat screen. Watch. We're deflecting the electrons. Again, you'll get a similar effect with a flat screen, but you may damage the flat screen. I would not do this with a modern flat screen. But if you find an old cathode ray style at a garage sale for $5, there's all sorts of neat stuff you can do with them. What's your question? It's so strong there. So I used to do a lesson on how TVs worked, but it was the old style of TVs, okay? The old style of TVs, the inside of the screen was coated with a phosphorescent paint that would glow when an electron hit it. No electrons are hitting there, no glow. It was the old analog ones were very clever and 1930s technology that worked great. It was pretty basic. We're going to practice a bunch of these now for the remainder of class. Again, if you feel better holding your paper vertically so you match my screen, fine. Or if you feel comfortable just keeping your paper down. A proton, it's a proton, enters a magnetic field along the line shown in the above diagram. What's the direction of the magnetic force? First thing I need to figure out is what's the direction of the magnetic field. Magnetic field lines point from what to what? So everybody, all of you, let's draw in some magnetic field lines. This is the magnetic field. Now, draw them in. This is everybody, draw them in. This is the magnetic field. This is a three-dimensional picture, so it's a bit tricky, but it looks like the proton is kind of going into the page. I'll do my right-hand motor rule. How do I know it's the right-hand motor rule? Because we have this and an external magnetic field, an outside magnetic field. So hitchhiker hitchhiker high five. That's a better way to remember it than hitchhiker handshake. You want hitchhiker thumb, high five. Okay, thumb into the page. Which way is the magnetic field pointing? Which way is the magnetic field pointing? The red lines, which way are they pointing? To the, I'm looking for it starts with the letter R. So for me, facing this way, I find it easier to go like this. I don't have to contort so much. Okay? I've got my thumb into the page. I've got my magnetic fields pointing to the right. What direction will this proton feel a force? A, B, C, or D? A, B, C, or D? A, B, C, or D? D is wrong. A, B, C, or D? Look at your answers in front of you. Don't be squinting to read the ones up here. D is wrong, because D would be towards that south pole.
The answer is B.
B, yes. B is in Bob. Try again. The above diagram shows an electron traveling to the right in an external magnetic field. First of all, let's draw in the magnetic field lines if they haven't done that. They go from north to south. It's an electron. Our right-hand rule does not work for electrons, but you will often be given electron questions because those are the particles that we can move around. So an electron traveling to the right is the same as a proton traveling which way? So point your right thumbs to the left. Which way is the magnetic field pointing? Down the page. For me, I find it easier to shoot my hand down here. Which way is my palm pointing? And is the correct answer A, B, C, or D?
A.
A, B, C, or D? I keep saying the letters. What is it? A, B, C, or D? I'm hearing two answers.
Sorry,
Which one?
B. I meant to say B.
Okay. There's going to be a bunch of those on this unit test in the multiple choice. We're going to practice a bunch, and I have a whole bunch for you to practice. I haven't found a way to do this, but practice. Okay, here, this is not the 3D one. This is not the solenoid one. I think this is the first one. Now, how can I tell? Let's read. Which of the following diagrams best illustrates the magnetic field lines around a wire carrying conventional current? This is the current carrying wire, the first one. What was that one? You pointed your right thumb in the direction of the current, and your fingers curled in the direction of the magnetic field. What direction is the current in these three pictures? Out of the page. So you're going to point your right thumb out of the page. What's the correct answer? A, B, C, or D? What direction is the magnetic field? Let's see. Out of the page, my fingers curl in this. It's got to be A. Ooh, I'm betting this is the solenoid rule. How can I tell? Because I see a picture of a solenoid. Very first thing I'm going to do is I'm going to complete the current. It goes down, and then I guess in the solenoid itself, I think it's pointing upwards as it goes. Yes? Okay. A power supply is connected to a solenoid as shown in the diagram above. The direction of the field inside the solenoid and the polarity of the solenoid will be, okay, let's see. I'm going to hold that solenoid in my hand. Callie is correct. Again, if you're not, Daniela, what you do with me? You're either going to hold it like this or like this. You're going to hold it so that your fingers curl in the direction of the current. So here's the question. Which side is north, X or Y? So, North Pole at X, yes, no, yes, no. And then we follow the magnetic field line, magnetic. What about inside the solenoid? Inside the solenoid, it's going from Y to X. No, no, yes, yes. What's the correct answer? Three more and I'm done. And then you have a fat ton of practice. A wire between two magnetic poles. Okay, this is the third one. How can I tell so quickly? There's a current carrying wire and an outside or external magnetic field, that big bar magnet. Let's draw in the magnetic field lines. They point from north to south. I always draw in a couple so I can see what's going on. What direction is the current? Well, if I look at this battery, it looks like the current is going, looks like the current in the magnet is going that way. So I'm going to point my thumb kind of into the page. Magnetic field is pointing to the right. What direction will this wire feel a force? A, B, C, or D?
B.
Down the page, B. Oh, this is kind of cool. A beam of positively and negatively charged particles enters a magnetic field as shown. This is one of the methods that we use at particle accelerators when we're trying to determine what types of charges we have. We send them through a magnetic field. We can easily figure out which ones are positive, which ones are negative. Let's assume this is a positive charge. So the positives are going this way. What direction is that magnetic field? What do those X's mean? So point your right thumbs to the right, fingers into the page. What direction will the positives feel a force?
Up the page.
What direction then would negative charges feel a force? So positive is yes, yes, no, 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 yes, no, yes. What's the correct answer? Gotta be B. I like number 15, I like number 15, I like number 15 because it's a trick question. It turns out a charge traveling through a magnetic field will only feel a force if it's cutting across the magnetic field. If a charge is going in the same parallel as the magnetic field, whether it's an electron or a proton or a wire, if they're parallel, there will be no force. It will just keep going in a straight line at a steady speed. It would only be if it cut across. Oh, and if it cut at an angle. Did I say angle? We're not going to do that, but it's not that hard to build in. So today was all about directions. On Thursday, we'll look at how to calculate the magnitudes, and then we can have both magnitude and direction. What's your homework? There's a bunch of right-hand rule questions here that you want to try. Every question is your homework. Thank you for your patience.